Hello everyone. In the last class we were discussing about the Liouiville's theorem, and we have reached up to this point where we showed that dou rho by dou t plus del dot divergence of rho v, that is equal to 0, where v is the velocity of the phase point, the representative point in the phase space. So dou rho by dou t plus del dot rho v, that is equal to 0. So let's find out this del dot rho v, the divergence of rho v. Okay, so what is v? V is the velocity that we know. Velocity is q1 dot e1 plus q2 e1 q2 dot e2 q3 dot up to q3n dot e3n. So these are all unit vectors. Okay, so velocity will have 6n components because there is q3n, q1 to q3n, 3n position coordinates, and p1 to p3n, 3n momentum coordinates. So the velocity, as we take the velocity, we have to take the first order derivative of q1, qi, and first order derivative of pi, where I changes from 1 to 3n. So the velocity will have 6n components. Okay, 3n position and 3n momentum coordinates. Its magnitudes are obtained by taking the derivative. So we have the q1 dot here and q2 dot, q3 dot. These are all e1, e2, e3. These are all unit vectors. Okay. So this is the velocity, and the del operator in this 6n dimensional space. See, we are considering 6n dimensional space. We know the form of del in 3-dimensional space, isn't it? Dou by dou x of I plus dou by dou y of j, dou by dou z of k, that we know. Here we are considering a 6n dimensional space. So del will be dou by dou q1 of the unit vector, dou by dou q2 unit vector, dou by dou q3n unit vector. So 3n components. The next 3n components, dou by dou p1 unit vector, dou by dou p2 unit vector, and final one, dou by dou p3n of dou by dou p3n, the unit vector. So this is del and this is v, and I have to find del dot rho v. So I multiply this with rho. So the entire expression, this is multiplied with rho. So I have rho v. I will have rho here, everywhere rho here, and then I am taking the divergence, that is I am finding del dot rho v. So as I take the divergence, I am taking del dot rho v. So I will have dou by dou q1 of rho q1 dot, first term, dou by dou q1 of rho q1 dot, dou by dou q2 of rho q2 dot, like that. Okay, so I will have 3n such terms for the position coordinates and 3n such terms for the momentum coordinates. So that is written here, sigma equal to 1 to 3n dou by dou qi of rho qi dot, then sigma equal to 1 to 3n dou by dou pi of rho pi dot. Okay, so here I have to take, if I take the derivative, I have to use the product rule, because rho is a function of qi and pi. So I am taking product rule here. So dou rho by dou qi dot plus rho dou qi dot dou qi. So here similar way, dou rho dou pi dot rho dou pi dot dou pi. So this is our del dot rho v. So that this I am giving here for del dot rho v I am substituting this. So I will get dou rho by dou t this term plus this one is this. Okay, there will be altogether 4 terms. Okay, there will be altogether 4 terms. So this is dou rho sigma equal to 1 to 3 and dou rho dou q qi dot dou rho dou pi dot plus rho sigma equal to 1 to 3 and dou qi dot dou qi dou pi dot dou pi. Now this one qi dot we know that is dou h by dou pi. Okay, the first 2 equations that we show with which the phase point is traveling through the phase space. Okay, the qi dot, the equations of motion, qi dot is dou h by dou pi. That when I give here, I will get dou square h. Qi dot is dou h by dou pi. So I will get dou square h dou qi dou pi. Pi dot is minus dou h by dou qi. So as I substitute, I will get minus dou square h dou pi dou qi. So these two are equal. Okay, the orders of differentiation, the only difference is the orders of differentiation, and that are same. So these two are equal and they will get cancelled. So these two terms will get cancelled. Okay, so we will be left with only these two terms, and that is dou rho by dou t plus sigma I equal to 1 to 3 and dou rho by dou q qi dot dou rho by dou pi pi dot, that is equal to 0. Okay, so next thing what I am doing is qi dot. For qi dot, as we did here, I am writing dou h by dou pi. For pi dot, I am writing minus dou h by dou qi. So sigma equal to 1 to 3 n dou rho dou qi dou h dou pi. Okay, dou h dou qi, this is equal to 0. So I have this Poisson bracket of rho h. This is actually the Poisson bracket of rho h. Okay, so I have this dou rho by dou t plus Poisson bracket of this rho with and h. This is something that we see in classical physics, classical mechanics. Okay, this thing is the Poisson bracket of rho and h. So dou rho by dou t plus bracket rho h, that is equal to 0. So this is our equation B and this one is our equation A. Now total time derivative of a function, which is a function of t, the time, x, y, where x and y depend on t. Okay, where x and y depend on t, that is the total time derivative df by dt, that will be equal to dou f by dou f dou t dt by dt. This is actually 1. So dou f dou t, partial derivative of f with respect to t, then partial derivative of f with respect to x dx by dt, partial derivative of f with respect to y dy by dt. Okay, so this is the equation. So d rho by dt, if I am taking total time derivative of our density function. Density function, we know it's a function of time, position coordinates and momentum coordinates. Okay, time, position coordinate, momentum coordinate. So as I take the total time derivative of this function, I will get dou f dou t plus dou f d rho dou t dt, that is equal to dou rho dou t dou rho dou qi. Okay, dou rho dou qi dqi by dt, that is qi dot, dou rho dou pi dpi by dt, that is pi dot. Okay, so I will be actually getting the total time derivative as equal to this dou rho by dou t plus sigma equal to 1 to 3 and dou rho dou qi dqi dt or qi dot plus dou rho by dou pi dot dpi by dt. So this thing, that the equation A is basically, this thing is basically the total time derivative of the density function. So this is the total time derivative of the density function. So from equation A, I can write the total time derivative of the density function d rho by dt, that is equal to this, that is equal to 0. Anyway, the total time derivative of the density function is equal to 0. So total time derivative of density function 0, or from this b which is actually derived from A, b is derived from A. So this thing is d rho by dt. So d rho by dt, or total time derivative of rho with respect to time, that is equal to dou rho by dou t plus rho h is equal to 0. So total time derivative of the density function, which is partial derivative of rho with respect to time plus the Poisson bracket of rho h, that is equal to 0, and this is the Liouiville's theorem. As we said earlier, what this means is the local density, or as we move with a representative point in the phase space, the density of the representative points around it, or in the vicinity of that representative point, that stays constant in time. Okay, so local density of the representative points as viewed by an observer moving with the representative point. Okay, as we move with the representative point, that stays constant in time, because d rho by dt, that is equal to 0, so rho is a constant. Okay, so we say the swarm of representative points, or the cloud of dust particles, moves in phase space in essentially the same manner as an incompressible fluid moves in the physical space. Okay, so this is the equation for the Liouiville's theorem, and this is the statement. Okay, so the representative points moves in phase space the same manner as an incompressible fluid. A fluid, if it is incompressible, what that means is its density cannot change. Okay, so it flows as an incompressible fluid in the physical space. Now we have to see the consequences of this Liouiville's theorem. So we know this is the Liouiville's theorem. D rho, the total time derivative of the density function, that is the partial derivative of rho with respect to time, and the Poisson bracket of rho and h, that is equal to 0. So this is what Liouiville's theorem is. Now if for a stationary ensemble, or for a system in equilibrium, we know for a system in equilibrium, actually we are always studying systems in equilibrium, rho does not explicitly depend on time. Okay, such ensembles are called stationary ensembles. So for that, this dou rho dou t, the partial derivative of rho with respect to time, that is equal to 0, because rho does not explicitly depend on time. So this rho h, the Poisson bracket of rho h, that is equal to, this is 0. Okay, right hand side is 0, so rho h is 0, Poisson bracket of rho h is 0, and Poisson bracket of rho h is, we know, sigma equal to 1 to 3, and dou rho dou qi dot plus dou rho dou pi dot, that is equal to 0. Okay, so Poisson bracket of rho h is equal to 0, and this is the Poisson bracket of rho h. Now one possible way of satisfying this equation, okay, is to assume that rho is independent of q and p as well. Okay, for stationary ensemble, for a system in equilibrium, we saw rho is independent of time. That's why we have this partial derivative of rho with respect to time equal to 0. Now for rho h equal to 0 to be satisfied, one way is to assume that rho is independent of Q and P. Okay, so anywhere on the phase space, okay, anywhere on the phase space, rho is same. Rho is a constant everywhere on the phase space. So rho does not depend on Q, rho does not depend on P. So here, as you take the partial derivative of rho with respect to Q, you will get 0, and here also, as you take the partial derivative with respect to P, you will get 0. So this equation is satisfied. So rho is independent of Q and P, or we can say rho of Q and P, that is a constant over the relevant region of the phase space. Okay, rho, the density of the representative points, that is a constant. That means the representative points or phase points are uniformly distributed, same density everywhere over the relevant region of the phase space. And what we have now is a micro-canonical ensemble. Okay, for a micro-canonical ensemble, this density is constant everywhere. Okay, and here, as we take the ensemble average of a quantity, if we are taking ensemble average of a quantity, that is, this is our equation, the fundamental equation, which is actually a function of time, because rho is a function of time, but we are considering stationary ensemble or systems in equilibrium, so it will not be a function of time. And additionally, for a microcanonical ensemble, this rho is a constant. Okay, rho PQ, that is a constant. So that will actually come outside. Rho PQT, since it is a constant, it will come outside the integral, and they will get cancelled, because rho PQT is present both in the numerator and denominator, and since they are constant, they will come outside and they will get cancelled. And what you get is this rho gets cancelled. So this is f of qp dq d3 and q dp d3 and p, integral d3 and q d3 and p, and the integration is over all the allowed region of the phase space. So that is this thing is written as the omega, the total volume of the allowed region of the phase space. So this will be the ensemble average of a physical quantity in the micro-canonical ensemble. So what you have in the denominator, it is the total volume of the allowed region of the phase space. Okay, total volume of the allowed or relevant region of the phase space. Now there is another way of satisfying this relation, that is the Poisson bracket or rho h is equal to 0. It can be satisfied by another way. That way is this. The dependence of rho on Q and P. Rho is not independent of Q and P, but it depends on Q and P. It comes only through an explicit dependence on the Hamiltonian. Okay, so rho does not directly depend on Q and P. Its dependence comes through the Hamiltonian. So rho explicitly depends on Hamiltonian. Hamiltonian, we know, explicitly depends on the position and the momentum coordinate. So the dependence on Q and P for rho comes through the explicit dependence on the Hamiltonian through Q and P. So rho of QP, that is written as rho of HQP. Okay, rho of QP is now written as rho a function of HQP. For example, we can have this. This is one example. Rho of QP equal to constant times exponential minus HQP over KT. Okay, so rho now depends on H, the Hamiltonian, directly, and indirectly depends on Q and P. So this is one example, and if we use this example and try to check whether this rho h is equal to 0. Okay, try to check whether this Poisson bracket or rho h is now equal to 0. So that is now checked. Sigma equal to 1 to 3n. Rho is this. Okay, for dou rho by dou qi, I am finding dou rho by dou qi. So dou rho by dou qi will be simply c exponential this. Then I have to differentiate this. Minus 1 by kt. Okay, I have to differentiate this. Minus 1 by kt dou h by dou qi dot dou h by dou qi. Then this qi dot which is present here. This qi dot. So dou rho by dou qi is this part. This part is dou rho by dou qi, and this part is dou rho by dou pi. Okay, same way, and pi dot here, and we know qi dot is dou h dou pi. Okay, qi dot is dou h dou pi, and pi dot is minus dou h dou qi. Okay, minus dou h by dou qi. So what happens is these two terms are equal in magnitude but opposite in sign, because a negative sign will appear here. So these two will get cancelled. So the Poisson bracket or rho h is equal to 0 is satisfied. Okay, so if I take rho of qp in this form, c a constant times exponential minus h qp by kt, then I will get the Poisson bracket of rho h equal to 0. So such an ensemble is referred to as the canonical ensemble. So these two ideas are very important. The Poisson bracket of rho h equal to 0 satisfied for equilibrium systems in equilibrium or stationary ensemble. That is satisfied for rho of pq equal to constant, which refers to a microcanonical ensemble, and rho of pq equal to c exponential minus h of qp by kt. This also satisfies the Poisson equation rho h equal to 0. So this is the expression for the canonical ensemble. If we are choosing the density function as this form, we will get the canonical ensemble. We will study in detail about systems in microcanonical ensemble and the canonical ensemble in later.